Good afternoon and welcome to the Mid-Year Energy Summit webinar series. Thanks so much for joining us today. My name is Jonathan Pierson, Energy Manager at Appalachian State University. Now, Dr. Lee Ball, who typically hosts these webinars, couldn't be here, but he asked me to do the introduction. Today is the first of the spring 2021 webinar series that's in conjunction with the Appalachian Mid-Year Energy Summit. So we've got a couple of upcoming webinars we just wanted to briefly mention before getting into today's topic. 2 weeks from now, March 4th, microgrids and battery storage. And then on the 18th of March, we've got embodied carbon in the built environment. But for today, staff from Western Carolina University and Appalachian State University are going to be reviewing recent heating, ventilation, and air conditioning, HVAC, operations in response to the COVID pandemic. So to introduce my fellow panel members, I just wanted to welcome David King, the Energy Manager at Western Carolina University, Greg Reese and Caleb Critcher, two of App State's top programming specialists in the Building Automation and Control Shop. And I'm Jonathan Pierson, Energy Manager at App State. So just a few notes before we get started. All attendees coming in are muted. And we hope to have an active question and answer discussion at the end of the presentation. So please use the Q&A function to ask questions. Also, this webinar is being recorded and will be available to view through the Energy Summit's website. So with that, I'd like to welcome my fellow panelist members. Thanks so much for joining us today.
Thanks for the invitation.
Great.
Thank you.
Well, as luck would have it, I'm the first panelist, so you're going to have to listen to me talk for just a little while longer. We wanted to start just by saying that it's our hope that this is more of an open dialogue. We're certainly not claiming any one best way to approach this. And certainly we also want to acknowledge the expertise of many people in the audience, and we're hoping you can help us with the Q&A portion. I started off this role, next slide, please. I started off this role as Energy Manager in April 2020, right as the pandemic was taking off. Thankfully, Appalachian's experienced and committed staff and leadership had an organized and effective strategy that we've continued to build and adapt. And just to set the timeline, the university's spring break in March 2020 was extended and eventually led to a shift from in-person classes to online learning. While faculty were transitioning to virtual formats, a significant portion of the university was closed. Most academic and administrative doors were locked, and there were very few exceptions for people actually working on campus. From an energy perspective, it was great. We were doing 3-hour daily building flushes to control humidity and prevent stagnation. But for the other parts of the day, our buildings were set to unoccupied. On really hot days, certain zones would reach their unoccupied cooling set point and the AC would come on for a little while. But for the most part, these systems were off for the majority of the day. And we were largely able to maintain this strategy through the end of July, which resulted in around $600,000 in energy savings after the COVID shutdown began. At the same time, we were reviewing as many articles, webinars, and guidelines as possible to prepare for students and faculty coming back in the fall. And it was a little challenging to determine what was more of a commercial for any particular must-have product versus a viable and scalable campus-wide strategy. And just a quick comment, when we're talking about this research, it's worth noting that time and time again, social distancing, wearing face masks, sanitizing surfaces, and washing hands has been found to be the most effective strategies for preventing transmission. But in order to increase safety, the university came up with a plan for our HVAC systems that was implemented prior to in-person classes beginning in August 2020. Before Greg and Caleb go into these specifics of operations, I'm curious, David, what Western's initial experience was like.
Yeah, so I mean, kind of to your point, Jonathan, we spent a lot of time just trying to read through a lot of ASHRAE recommendations. So for those of you out there not familiar, ASHRAE is the American Society of Heating, Refrigeration, Air Conditioning Engineers. And many of the recommendations that you see the CDC making are based on, certainly on mechanical systems, are based on ASHRAE. But to go back one step further, when Lee Ball had reached out and kind of contacted us about kind of doing a presentation on how we approached COVID response. You know, his timing was perfect because we had just delivered a presentation to the chancellor and her executive council. And, you know, then as is today, that the intent was for the chancellor was to show not just what actions we had taken to show that we'd been responsible, but also to kind of give her and the decision makers a better understanding of the systems involved. And that's kind of the intent for today, like just to kind of show everyone what goes on behind the scenes and what's involved. You know, it's definitely, you know, she was very gracious and thankful, and I think she realized that there's a lot more than just turning on and off the AC. And so that's certainly one of the goals for today, just to kind of increase the awareness of what happens behind the scene. But yet, going back to what we were doing at that time, you know, like yourself, we were trying to read up on as many articles as possible, whether it was ASHRAE and as well as APA. So APA, for those of you not familiar, is the Association of Physical Plant Administrators. And they had some fantastic webinars, and one by UNC Systems' own Alan Boyette. So just to kind of give you an idea, again, of how much a director is responsible for. So Alan covered, you know, not just the HVAC in his presentation, but all the housekeeping response, signage response, and all the duties that he had to cover. And, you know, one just side note real quick, that one of the numbers that sticks out to me at Western, we have a 2-man move team, and those guys moved 3,000 pieces of furniture on campus, pulling chairs out of classrooms. And even when you go to the rooms, you can see the stickers of where the chairs have to be. Just unbelievable amount of effort involved. But so anyway, you know, I reached out to Alan after watching his APA presentation, and he was very gracious with his time. And, you know, one of the things that really kind of resonated with us that NC State was doing was they just wanted it, you know, they knew by the time fall started, there's no way you can go through and get to all new technology across campus, putting in UV lights or bipolar ionization. So, you know, I thought their approach was very realistic in that let's just get our existing equipment to operate properly. And I thought that's kind of the points that we have down here. Are our systems operating correctly? And it kind of resonates with just, you know, let's be realistic about what we can do. So, and behind a lot of those ASHRAE and APA recommendations, that second bullet there, basically you're increasing the amount of outside air, which is the dilution, while trying to maintain humidity levels. So that's that. I'll leave it at that unless you have anything else to add, Jonathan. I think Greg.
Yeah, that was great. We thought it might be helpful for some watching if we walk through just a really basic overview of how a typical air handler works before diving into specific changes that were made for COVID. So without further ado, Greg Reese.
Yes, good afternoon. My name's Greg Reese. I'm with Appalachian State. And my objective is to show an air handler how it operated before the COVID, so you can understand the changes that we have made to try to deal with the COVID. And this is a basic graphic of an air handler with a reheat system, which is most commonly what we have on campus. And I would like to explain the air pass. If you look in your space, the grill, the supply grill that normally has noise, or you can feel the cold or warm air coming out of, it comes from this duct right here. This is your supply air duct. And the grill that's in your space that normally you don't hear anything out of is actually the return, and it's coming back in this ductwork right here. This is the return fan and the supply fan. Now you'll notice the supply fan only has 2 choices of airflow to actually bring to your space. And one of those is return air and outside air, fresh air. So your question may be, well, why do we even use return air? Why don't we always go outside air? Well, it's expensive. And if it's a cold day, you've got to heat all that CFM up to whatever you're trying to discharge. Right now, we're trying to discharge 63.8. So if it's below 63 outside, the more of this outside air that we bring in, we actually have to heat it up. And but we have to have a minimal outside air to maintain ventilation for the people and also building pressurization. So we have to have some outside air, but the return air, there's times when it's so expensive that to use the outside air, we'll go to minimum and use as much return air as possible. And that's when the latent energy, the total energy, the sensible and latent energy of the outside air is higher than return air. We'll go to minimum. Or when it's really cold outside, we'll go to minimum by backing down until our mixed air temp is at its set point. And so there's some things that we have in the system to help treat this outside air, even when the minimum's too cold. We have a preheat coil. And when we're using minimum outside air and it's too hot, along with the return air, we have the cooling coil. But there are times, like if we were asking for 63 and it was 60 degrees outside, we may be 100% outside air and be supplying the exact discharge air temp we want and not be using any return air. And when we do that, we have to have an exhaust. And that's what you see right here. When you're bringing in so much outside air, instead of letting the windows whistle and the doors push open, we exhaust it out of the building. So one last thing I'd like to talk about is our actual discharge air reset. And we actually change this set point depending on the number of VAVs that are in cooling or the return air humidity percentage. If the return air humidity is above at 60%, we ask for 55. If it's below 55%, we ask for 65. But we use the grader of either the humidity or the cooling demand. If we usually use 30% of the VAVs served by the AHU as the high. So if 8 VAVs is asking for cooling, we'll be at 55. And if less than or zero is if we're at 0, then we're at 65. And you can see we have 1 VAV in cooling, and we're actually asking for 63 because our humidity is low. I think that's it. Next person.
Yeah, my name is Caleb Critcher. I work at ASU along with Greg, and the slide that has been brought up now is the same graphic that Greg had before, but some of the values have changed a little bit. So I'm going to go over that. And along with a lot of other things in our life, I mean, COVID changed a lot of things for us as well. At the controls office, our workload definitely went up. And we also found ourselves working systems in what would be considered a non-standard operation, like Greg just went over. So what exactly was our response to the COVID situation? Well, what the decision was made was to operate our standard unit more like a dedicated outside air unit in order to flush the buildings and in order to dilute the inside air with as much outside air as possible. In hopes that it would reduce the COVID transmission. Well, exactly how do we go about doing this? This is going to be a campus-wide change to many different systems. So we got together and talked about how we're going to do this. Well, we couldn't just necessarily go through and lock open our outside air dampers. That would create, a lot of problems and issues, and we would have no control over it whatsoever. So we knew we had to do this from a programming standpoint. We could do it in the lower level, the local controller of each individual unit, but that would be very time consuming. And if any additions or changes needed to be made, it would also be time consuming, be a little bit more difficult to control. So we decided to utilize our higher level building automation system programming applications that we have that would basically override anything going on at the local level of the controller. So we can take control of certain aspects of the unit, but maybe not necessarily all of it. So we got together and standardized a sequence and a program that was both efficient and would be consistent across campus. And this program needed to be able to allow us to make any changes as we deem necessary, options to manipulate it for any kind of mechanical differences that we had, or maybe building needs. A lot of these systems use different types of heating and cooling. Some of them are very, what you would consider analog, like this system uses chilled water in a coil and steam in a preheat coil. These are very analog, but sometimes we have electric heat. Sometimes we have like a heat pump or a DX cooling. Those are very binary. And so those things all change the way that the system operates. So we had to be aware of that as well. So exactly what were the changes we made? Well, so we want to span the outside air damper open towards 100%. And essentially the way we did that was by changing the minimum outside air flow set point to the max, which in this situation is 5,000 CFM. Well, we also want to maintain the temperature and humidity control in the building. So our discharge air temp reset is going to remain active, that part of the program. The preheat temp reset is going to also remain active. We are going to disregard the mixed air temp and disregard any kind of demand control ventilation going on. So what happens is we span our outside air damper open, and it's going to allow as much fresh air in as possible. It's going to follow down into the duct system, into each individual space. And then as Greg said, that the return out of each individual space is going to come down our return duct, across the return fan, and then exit it out of the building. So we want to maintain this cycle of pushing outside air in, drawing inside air out, and exiting it out of the building. So doing this, Greg also talked about the differences in outside air temperature. It could affect the system. So now also we have two control processes. We have a control process on the outside air damper and possibly our preheat or our cooling coil, two control processes trying to affect discharge air temp. And that can create some stabilization issues. So if we notice something like that, we would go into the program and make those changes as necessary. But as we bring in, let's see, in this case, this SNP is showing a very high discharge air temp. And you see that our set point is 55. We're trying to maintain 55. Our discharge is higher than that. We are trying to cool that outside air, that warm outside air, with this cooling coil. Well, we're not able to do that. So because our cooling coil is not able to meet that demand, we need to back off this outside air damper just a little bit. We're going to try and meet some sort of stasis, some sort of equilibrium there by backing off the outside air damper, so we can actually maintain the discharge air temp control. And the opposite would be true if it's cold outside. We're going to look at this preheat temp and this preheat coil. And if it gets overloaded, again, we're going to back down the outside air damper. So that's basically how it works. So obviously this is putting a high demand on our systems. They're not generally designed to run at this type of load, since we're forcing so much more outside air in. So this may expound some issues, mechanical issues, or incapabilities that this system has. And also it's going to illuminate maybe some mechanical maintenance issues that you didn't realize that were there. So from a maintenance standpoint, it could be actually useful to run the system at max, it eliminates those issues. You can go in there and solve those problems. And also, obviously, as it was mentioned, this is going to consume a lot of energy. It takes a lot of energy. You're using fossil fuels, you're using more electricity. So this definitely is going to be an energy issue. But the good news is that a lot of our school semester falls in the spring and fall months. And during those months, we have more temperatures that are more conducive to the type of temperatures we want to maintain in the system. So we're able to actually, what we call economize with the outside air, because it is actually closer to where we want it to be. So it's not always an energy hog, as we like to say. A lot of times that outside air is beneficial. So our team did a great job in coming up with this program and monitoring the system for issues and implementing any changes that were necessary. And we were really happy with the way that it came out. Next, please.
Great. Yeah, thanks, Caleb. That was a fantastic description of your guys' systems. So just kind of share some of the things. Just go back one slide. So, you know, in our approach at Western, we were looking at what could we scale across campus. And so one of the things that we could scale, so our campus, we're about approaching 3.5 million square feet. About 2/3 we have under some level of building automation system. The other third might be pneumatic and whatnot. But so we're really trying to figure out what can we scale across campus that, you know, regardless of the building age, we could have some sort of response. And one of the ASHRAE recommendations was to extend your HVAC hours. So the idea here was just to kind of turn the air in the building over, right? So if you look at the slide here, this is actually for our admin building. So you can see that it used to run from 7 a.m. till 8 o'clock Monday through Friday. And so a pretty quick and easy fix here just to add those 2 hours, right? So now it runs 5 a.m. till 10 o'clock at night. So we had this ability, like I said, across about 2/3 of campus. This was kind of a no-brainer, and just kind of points out that the capability of a good BAS system, that we were able to do this in, I mean, probably about less than 2 hours or less to do this, scale this across campus. You know, on the kind of in the bottom there, you can see an example. I just put in a snippet of one of our fan coil units. So, you know, as Caleb and Greg have really pointed out, like that it's, you know, some of the equipment behind the scenes. So we were actually measuring. You can see that, you know, going from left to right, you can see there's a little X there that actually monitors airflow. This is down at the zone level, right? So this would be serving maybe like a classroom or a couple of offices. So even down at that zone level, you know, we're actually monitoring airflow as well there. So if we have some sort of issue, we'll get an alarm, and you can see the air passing through the heating coil and heat it up to 114 degrees. So again, I think, you know, once you kind of get used to the abilities of these systems, it's kind of hard to go back, certainly. Next slide, please. Most of our systems, though, that's kind of our latest and greatest. That's our preferred control system. But about another, you know, 1 million square feet of campus is much older. You know, so we've got a lot of 90s technology, which looks like the graphic you're seeing right here. So in this example here, you know, Caleb and Greg have talked about outside air dampers. You can see one here at 10%, right? 10% open, but that's just what the program is telling it to operate at. And without that airflow station, we don't know what it's actually at. You know, if you have a good understanding of the systems, you might see, you know, okay, I'm looking at the return is coming back at 66.9. And, you know, if I'm coming down and to the right, I see 58. So it's, you know, got to be cooling from somewhere since I have 43-degree air. So, but there's no substitution for, you know, without an airflow station, you know, to go into the physical unit. So that's you know, going back to Alan Boyd's point of like functionally testing all your units. So and that's what we did. So we went through 124 of our air handlers, and we did a functional test. So what that involved was from the software, taking that minimum outside air and from the software commanding it, hey, go to 100%, and now go back to 0, and actually seeing if it did modulate, and also looking at the return damper. It should be interlinked. As one goes to 0, the other can go to 100. That's kind of a standard setup. So just because it says it on the screen does not mean it's actually going there. The control system, it'll send like 0 to 10 volts to this electromechanical actuator, which has little small gears within it, and it'll actually physically drive open that damper. And you can see here, we had about a 25% failure rate. So, many cases that was the actual actuator. So that was one of the common things we found on those systems. And without an airflow station, you wouldn't know that. The other thing we found a lot, this is particularly on the older 90s software, we don't have all the access to the programming. So we would try to send it to 100% and then nothing would happen. And we realized we had to actually call in the controls vendor, wait for him for a week to show up, and he's driving out of Greenville, and super helpful guy, but we're still on his schedule. But what we found was just a lot of broken links within the software. So, you could tell it at the server level, hey, go to 100%, but it wasn't making it down to the controller on the air handler. So that was probably the most complicated thing we had to resolve. And 25% sounds high, and we actually had, I don't know if we're any better or worse, but I'll point out here, we had part of our PM program, our HVAC mechanics, they'll go through the air handlers and do a visual inspection on the dampers, right? When they go through and they'll grease all the fittings and whatnot. And, they're looking for making sure the dampers weren't cracked or compromised and all the seals were good. But really, I think the lesson we took away from this is you really need ourselves and the control shop involved in this to do that test. So we kind of discovered some gray areas in the whole process. So that was certainly a good takeaway. And so, one last thing I'll add to this, and that we've never, and I don't think certainly Greg or Caleb have received this complaint, but no one ever calls facilities saying that, hey, I don't have enough outside air. It's, if you look at the system here, it's got the cooling coil. It says DX cooling, it's in line. And as long as that cooling is working, you're not going to get a call. The calls are going to be, it's too hot or too cold. So your outside air can be completely closed for years. And as long as that cooling is working, no one, you're never going to get that phone call. So I think this whole, there's a silver lining to COVID. It certainly brought those issues to light. Next slide. One other thing we did, just kind of adding to kind of piggybacking Caleb and Greg's information. So we disabled demand control ventilation. So that's certainly a mouthful, but it's basically it's a energy saving strategy. So if you're an engineer and you're sitting down to design a new air handler, you'll look to ASHRAE, and there's an indoor air quality standard 62.1, and what it'll look at. So for like an office building, they look at everything from like metabolic rate of the person and the space. So for somebody working in an office admin building, they say, hey, this person needs 5 cubic feet per minute. So a cubic foot, if you can imagine, 1 foot by 1 foot by 1 foot, that's what they required per minute. So that's per person. So if you have 100 people in that space, 5 cubic feet, that's how you come up with the math. And then you also need 0.6 CFM per foot of the space. So this accounts for just kind of off-gassing of furniture, carpets, and bioeffluents as well. So that's certainly, if you haven't heard the term IAQ, you're probably going to hear a lot more about indoor air quality. So you can see on the top left, you can have one set of dampers, or you can have a dedicated set. So here in this system, we have a dedicated minimum outside air set of dampers. And you can see as it comes, it's wide open. One of the things we discovered, if you look in the bottom here, kind of the center of the BAS, you can see we're looking at CO2 as well. So the energy code says if you are, so it's like I said, the engineer is designing for a worst case scenario. So, but you don't really need to run it at a worst case scenario for reasons that Caleb and Greg have mentioned. You'll create all kinds of humidity and pressurization issues. So if you're looking at your CO2 within your space, you can actually reduce the amount of outside air. And that's what we mean by saying demand control ventilation. So one of the things in going through this process, we realized, you see here, we have average CO2. So if we have 10 spaces that we're looking at the CO2 within that space, you can have one zone that gets pretty high, over like 1,000 or so. But if you do the math, that's not going to open up your outside air. So we realized we had to really look at the max CO2 from all 10 zones. Whatever came in, whatever with the max from those 10, we needed to drive that outside air. So that was certainly a takeaway from this process here. Next slide. And one other thing we've invested in over the years is just more and more in-house training. So here's our controls technician, Dwayne, and he's doing some. We've tried to ramp up our training on TAB. So this is test, adjust, and balance. So what we're looking at here, Dwayne has got a digital manometer, and he's actually measuring different air from on the supply side. So there's little actual ports drilled in here, and we'll actually measure, create a kind of a matrix of air measurements and use that to calibrate these airflow stations, right? So think of the ones that's shown earlier in the presentation, and you can see the ones on this slide, one's at 0, the economizer, because there's no calling for cooling. And then the one above at the minimum outside air is at 1100. So that's, the newer abilities as we get new control systems, we've gone through and calibrated the systems ourselves. And it's certainly, it's not only just saved us money in terms of hiring a TAB contractor, but it's certainly brought more knowledge in-house and given us a better understanding of the system. So we did a lot of that training. I'll just mention that through the University of Wisconsin. So it's a continuing engineering series there. So we actually went to Wisconsin for a week training. Certainly money well spent. And I'll say that. Next slide. One other thing we did across campus, and credit to the HVAC team here and our director of operations, we really, something we could do on these older buildings that are all pneumatic that we could do across all of campus was to increase our MERV rating. So MERV is minimum efficiency rating reporting. So, the example you're looking at here on the right, you've got Kevin, one of our HVAC mechanics, and the cabinet, the doors he has open here, the air is moving from right to left. So what you want to avoid is filter bypass. So, this is a newer system here, but as that door on that cabinet is closed, you want that door to be flush up against the filter. And on a lot of older systems, that may not be the case. So air is going to take the path of least resistance and just bypass that filter. So they went through, in a lot of cases, they had to add like metal blocking just to make sure the air didn't have a pass to go through. This one you're looking at here is a newer system, so it's quite flush. And the other thing that we did was to just incrementally increase the MERV rating. So here, if we had MERV 8, we went to MERV 9A. If we had MERV 11, we went to 13A. So we didn't want to create any kind of capacity issues. If you can't just slam in a MERV, go to MERV 18 or a HEPA filter and not face some consequences and create some new humidity issues or reduce the airflow. So a lot of the systems may not be designed for that. So we just did a small incremental increase. And again, we like this because it was something we could scale across all of our buildings, everything with filters. And so the A there denotes that as the filter over time collects dusts and loads up, that it's maintains its efficiency. So how much of that is sales and marketing? That'd be a good question, but that's our understanding of it. So we ended up investing in about an additional 3,800 filters. It was 3 transfer trucks, and if you go to our mechanical rooms, they're just stuffed full of air filters everywhere. And so every day those filters are checked. What the HVAC mechanics will do, they'll take that same digital manometer from the previous slide, and they'll actually, if you look at the graphic here, you'll see a dirty filter in the middle. So what they'll do on buildings that don't have this ability, they'll actually take the hose and they'll measure both sides of the filter. So initially, let's say it's 0.3 inches. And as it gets dirtier over time, there's going to be a greater pressure difference between the side of that filter as one side gets dirtier. So once it doubles, that's when they change the filter. So if it starts at 0.3 inches and when it gets to 0.6, that's when they'll pull it out and change it. The graphic here, we've got this automated, so it can show up, here it's showing a little red dot kind of in the top right is an alarm. So it's showing up dirty there. So some places we have this automated on newer systems, and some places they have to physically go check it in person. Next slide. And so, again, kind of circling back to what Greg and Caleb have already mentioned here, we certainly, one of the things I took away, there's a Taylor Engineering has a fantastic paper out there, but, one of the things that they've brought to light is just, you don't want to create new issues. So, what we liked here is that you really want to try to maintain your humidity setting between 40 and 60%. You know, if you start to go much below 40%, you're creating, you can see here, more of an environment for viruses. If you get above 60, you're really creating a haven for molds and whatnot. So that we, you know, so again, we're trying to ensure that we have proper dilution while controlling humidity. And just to kind of it's worth reading, but just to hear ASHRAE's position. So the most unfavorable survival for microorganisms is when humidity is between 40 and 60%. So we're trying to keep that in the back of our mind the whole time as we're trying to increase air. So, and I think Kale did a good job of demonstrating, trying to find that balance. Next slide. So again, lessons learned. I mentioned this earlier. So we definitely have this on our PM schedule now that we certainly need to do a functional test, go to each air handler and see if those dampers are physically working and not just rely on the software to tell us that it is. And the other thing, had this on our sites for a while, but this was the good time to pull the trigger. So we created a summary page of our chillers. So we don't, like some larger campuses in the UNC system will have a central chiller plant. So we don't have that. We have distributed chillers pretty much by building. You know, maybe the largest one chiller provides building cooling to 3 or 4 buildings. So you may be asking, what do chillers have to do with outside air? So, you know, under ideal conditions, if you have cool, dry outside air, you should not need to run your chillers, right? So if it's 55 degrees outside, and you should be able to use that for cooling. So we've created a summary pulling in 10 of our newer control systems, 10 of our buildings. And on the left column, you can see outside air temp, OAT. And it's, you know, somewhat anywhere from mid 50s up to low 60s. So we should be able to use our outside air, the economizers. We should not be seeing any of these chillers on. If you go to the third column, you see enable, and there's only one that's on. And see that's for Balsam Chiller 1. And you see chill water supply is actually at 44 degrees. And so you'd have to know, so what's going on there? So that chiller actually does supply chill water to our dining hall. So you can imagine, not surprising, dining hall, all the cooking needs there would need additional cooling. In reviewing this, kind of going through the slides the other day, I noticed something I missed the first time and presented to the chancellor. There's one other culprit here. If you look down to Madison, the enable status is off, but the chill water supply temperature is 43. And so sure enough, I followed up with the HVAC mechanic, and they have had some issues. They've had to run the chiller, put it in hand, basically, because of some issues they've had with the makeup air there. So this has certainly been helpful. Our controls tech now, he can pull this up and look at 10 buildings in one glance. So it's definitely the direction we've been going, and we've done the same thing on the heat exchanger side too. So it's been a good way to kind of take a quick snapshot of what your systems are doing across campus. Next slide. I don't know, Jonathan, if you want to step in here to talk about some of the common questions, and we can kind
of. Yeah, that'd be great. That was a great review of all those strategies. I think it was nice to lay them out. We want to talk about some of the common questions that we hear, and quite understandably, before and after classes had resumed, we were getting quite a few questions from students, faculty, and staff about particular buildings. These questions listed here seem to be the most commonly asked, and we just wanted to give our perspective on the general answers. So this one about number of air changes per hour in a particular space. For some of our newer buildings, we can somewhat reasonably calculate that number for a specific area, but on a large scale, that's quite a task. And for many of our older buildings, it's a difficult answer to come to. Without going to each room and physically measuring supply and return ducts under a variety of different outside air temperatures, our best next option is to rely on as-built drawings, and then we're really only providing a best case, worst case estimate. So in the beginning, and we continue to try to work with folks who want specific estimates, but we're also focused on developing and implementing a campus-wide approach, and we've been trying to keep that in mind. For this next question, should I open my window? And that's a tricky one, because if we're saying here dilution is the strategy and more ventilation is better, then why shouldn't we open windows? And it's a hard argument, because for that one particular space where you're opening a window, you might be increasing ventilation. But if you're looking at it from the whole building perspective, open windows really can impact how a system operates. And we've really focused on ventilating the entire building for as many people as possible, rather than just one space. And Caleb, I know this is something that you've been seeing in some of our buildings.
Yeah, that's right. We see where this potentially can cause an issue with our discharge air temp reset program. If you have an outlier zone that's too hot or too cold because of an open window, that can definitely affect that. Also, it can affect the return air temperature, and it affect the downstream system that the air handler is trying to control. And when it's already running at its max, and these temperatures are coming down the return duct from an outside air situation coming from inside the building rather than from the air handler itself where we're trying to control it, we've seen it actually back off the outside air damper. And so you're losing more outside air to the rest of the building rather than just that one zone. And also it can affect pressurization issues. And you can change the pressure dynamics of a certain floor or a certain zone and push air in different ways and maybe lose some building pressurization from the air handler. So yeah, it's definitely caused a few issues that we've seen.
It's a tough one to answer because it does make sense on some level, but then from the whole building perspective, it does cause some
I would just say, John, I would just say too, I know you guys probably the same. We find a lot of, as we shut things down at Christmas time, we find a lot of open windows across campus too, which can be expensive when you start bursting pipes. So that's
sure.
Which has happened before too.
Absolutely. And this last one about energy savings, I'd say at least once a week, probably even more. I hear a comment or a question about how much money the university must be saving with most classes being online. And even with 75% of our classes strictly online, the remaining classes are either on campus or they're a hybrid with some in-person component. And so campus has to be open. When we're in that economizing sweet spot that Caleb mentioned during the fall and spring shoulder seasons, we're seeing energy savings, but that's typical for any given year. But as soon as the weather gets cold, our buildings become more energy intensive when occupied. Next slide, please. So just to walk you through our experience here at Appalachian State, this timeline takes us through that April 2020 shutdown that I mentioned. It helped App State reduce energy use significantly. And then when classes resumed in August 2020, when we had the COVID programming up and going, we were keeping a close eye on energy usage in relation to COVID. But we saw warmer temperatures in August, kind of the end of summer, bring brief but significant increase in air conditioning related electrical usage. But that was pretty brief. And then we went into these shoulder seasons and our COVID operations kind of functioned as our typical ones would, as David and Caleb mentioned. But the shift in energy, not surprisingly, occurred when outdoor temperatures started to drop. We were using more steam to heat buildings with colder incoming outside air. But at the same time, our daily class schedules were significantly shorter. So even with this 2-hour pre and post dilution strategy, when we were having classes that would typically meet in the evenings or weekend classes, spaces that might typically be open until 10 p.m. or even midnight, we're closing at 7 or 8 p.m. So we were still able to squeeze daily HVAC schedules, even with that extra pre and post dilution. And then the thing that really helped us was instead of students coming back for Thanksgiving for exams, they were online and the university was largely closed for a month over the holidays. This undoubtedly reduced COVID transmission of people going home with their families and coming back and traveling and everything. But it also allowed the university to implement a 55-degree unoccupied set point for the majority of the buildings. All this to say is there's been drivers both increasing and decreasing our energy use. For everything that's going on, it doesn't necessarily reflect everything at play on paper. Our steam use, our heat, has been relatively consistent with last year's usage, but this holiday break that I mentioned helped us capture savings. So we're now about 4.5% less than we were last year. Electricity's been pretty steadily about 10 or 11% less than the previous year, and that seems most likely associated with the reduced lighting, with most classes being online. Predicting the future, is challenging, and so it comes back to this original question of how COVID is affecting energy costs. We've been able to reduce energy consumption, but depending on how long the pandemic continues, we're likely to start seeing electricity increase as hot weather drives increased air conditioning demand. Next slide, please. So just one final thought before we open this up for questions. We just wanted to circle back to this basic importance of distancing, wearing masks, washing hands, and sanitizing surfaces. The Taylor engineering white paper that David referred to did a really thorough analysis of over 200 reports, and this graph is from there, and it shows what would have to happen for COVID to be transmitted through an HVAC system. And while we're certainly not minimizing the risk, Taylor Engineering put out this thoroughly researched paper late last year and had yet to find a case of air handler transmitted COVID. It's not to say that there haven't been any or there won't be any, but it does just highlight the importance of circling back to these basic effective strategies. And with that, if there's no other comments from our panelists, we can open it up for some questions.
I'll just add real quick, Jonathan, kind of to your point too, this was one of the questions we received a lot of, how people worried about their next door neighbor's office. Can the virus be transmitted, rebroadcast as an aerosol? But I think this graphic well kind of sums that up, and it would have to travel through the whole air system. And as we know now, just maintaining 6 feet and controlling the source, a mask, is really, there's just no substitute for that. So, with our energy numbers too, are pretty in line with you guys, pretty similar steam usage. We've got a central steam plant like yourselves, and our electric use is about a 20-25% down per month. And it's, you could write a whole research paper onto why or why not. It's like you said, there's so many variables. I don't know if it's, I think the city of Boone is built around App State, and where Cullowhee, we're pretty much the university. I think if people aren't teaching or on campus, they're, we're a little more remote, so they may not literally be on campus, but I'm speculating at best, so it's curious, but that's kind of where we're at too. I would have thought here running the buildings longer, we'd see an impact, but there's just fewer people in those buildings, so.
Great. Yeah, there's certainly a lot to it. So we've got a few questions coming in, and please feel free to ask away. But for this first one, what can be done for buildings with no central HVAC systems?
Well, I know we've got I'll jump in here, but we've got a vaccine clinic starting up next week, and what they've added there, they've added these kind of portable. I'm not sure if they're a HEPA filter. So a HEPA would be basically anything that's rated at MERV 18 or greater. So it doesn't provide fresh outside air, but it just kind of removes the particulates from existing air. So, how much of this is just kind of allays people's concerns, but the person that came out and pitched this to our director of operations, he was showing a test, and I wasn't there, unfortunately, but he was showing a test to show that how it was able to remove less particulates from the air, before and after. So it's kind of a standalone unit. I think it was Camfield, like the same company that makes air filters, Camfield. So I think with that vaccine clinic in place, they've got those stationed throughout. And this building is one that have new controls on, has outside air. So I think we've kind of gone above and beyond there. So.
Sure, it's a challenging task for sure with limited options, and those portable units are certainly expensive and difficult on a wide campus-wide approach.
Yeah.
So we've got another one here about, as a general approach, recommendations from ASHRAE and CDC to increase ventilation air is intended to reduce potential concentrations of aerosols within the spaces. Another way to reduce concentrations of aerosols is to reduce the amount of people within the space, which we've done in a lot of our classrooms to maintain social distancing. Understanding that more is going to be considered better, how are others balancing these two concepts? And that's a great question, and just thinking of the balance of less occupants and more ventilation. And if you walk around in some of the classrooms at Appalachian State University, you'd see the facilities group here did a lot of work in wrapping class chairs and cellophane wrap to physically make it so that folks were sitting further apart. And when we're looking at our occupancy numbers for any given classroom, they're certainly less than there typically are, but those are changed to ensure that 6 feet of space is available. Would anybody else have anything to add to that? So this one came in, sorry, go ahead. This one came in for Greg and Caleb. If space humidity increases above 60% during times of high outside air dew point conditions, is the minimum outside air set point adjusted manually, or is it the reset auto?
If the space humidity goes up to 60%, and I mean, there are a few buildings we have space humidity sensors, but mostly we use the return air humidity. But either way, if it's at 60%, our discharge air temp reset is asking for minimum 55-degree discharge.
Okay. So would you say that that's more of the resets in an automatic function?
Yes, it's an automatic function. If the humidity's at 55% or below, our humidity part of the reset is asking for 65 degrees. If it's between 55 and 60, it ramps up it ramps down the set point from 65 to 55. By the time it gets to 60%, we are at the lowest set point of 55 degrees.
Okay, great. David, you might be able to answer this one. What are the thoughts about continuing to drive energy use intensity down after we return to normal campus occupancies, given that we'll likely continue to increase outside air and air exchanges?
Well, I mean, it's certainly finding that balance. Our strategy, I think, right now we're using energy savings money, 1292 carry forward to replace old systems. So I think you can definitely have both. I think you can definitely continue to do your functional testing. You may have to increase your outside air, but I think you can have a lot of other strategies in place to keep driving down that EUI. One thing, full transparency, I just discovered this recently. So our buildings, again, trying to coordinate. We have a campus policy we are reworking. So it's been brought to light, and I wasn't the only person surprised, but that we do not have classes on Sunday. So trying to meet the needs, match the HVAC schedule to the building needs. It takes a lot of coordination. And so we're trying to hammer down a campus policy for locking those doors on Sundays. And once we kind of have that in place, we could certainly pare back on the scheduling there and running the HVAC. But again, with COVID happening right now, energy savings is out the door. We're not going to risk any kind of reduced ventilation. So no, it's a good question. I think you can do both. I think that's what we strive to do.
Yeah, I think the only thing I would add to that is that with this outside air, and then there's also balancing this with the humidity concerns, and finding that we're not always going to be bringing in outside air. That there can be both. To find that sweet spot of the minimum likelihood of transmitting, we can also maybe back off our outside air and focus a little bit on energy savings.
I'll just add, I'd heard lots of good things about Jonathan, the new energy manager there, and I was joking with Jonathan. I was like, once you guys get into these savings, you're going to be fantastic. People are going to want to know how you're going to recreate this next year, So try to.
Yeah.
All eyes are on you, Jonathan.
Yeah, COVID has been a very serious thing, not to laugh at it at all, but it has had some ancillary benefits, I guess we could say. We do have a couple of requests for some follow-up written items from some of our presenters here. David, we've got a request for asking about your SOPs for your functional testing. Would those be available? Would you be willing to share those?
Sure, yeah, standard operating procedure, I'm guessing.
Yeah.
Okay.
And then, we're also asking Greg and Caleb, had some interest in just following up on some of the strategies that you described in our COVID operations, and hoping maybe that we can put a little bit of text to them and share them with the attendees as well.
Yeah, and I think I'll just say real quick, John, I think that's the benefit of what you guys have created at App State, just this kind of a environment to kind of share these, best practices or worse, things we've discovered that we need to change, So that's, credit to you guys for creating this environment. And certainly, no one here is, the only people I don't trust are people that consider themselves experts. I think we're all still learning. So.
Absolutely. Still a learning process. And with that, if we don't have any more questions, we can go ahead and conclude. But as our time together closes today, I just wanted to thank my fellow panelists and all of you who attended for taking time out of your schedules to join us. And please sign up for the next webinar in 2 weeks on March 4th, entitled Microgrids and Energy Storage. Thank you again, and stay safe.
Thanks, guys.
Thank you.
Enjoyed it. Thank you.